Yeah, that was Alex. Hello, everyone. We're very happy today to have Kasha in our group meeting to present his work. So, Kasha will final year PhD with autonomous vehicle group in University of Tübingen, Germany. So, supervised with Andres Geiger. Before that, I did a master in CMU, and during the master study, I learned that media and currently is co-organizing workshops on driving in Eastern Asia and Italy. So you can find more information on his website. Yeah, so today, Kasha will talk about imitation via abstraction and planning. So welcome.
Yeah, so thanks to Hafe for fitting me in last minute. Yeah, I think I get started. So I'm Kashyap. Yeah, I'm at the University of Tübingen, supervised by Andres Geiger, and I work on self-driving. Today, I wanted to go over a bunch of things. First, I will talk about transfuser, which is one of our previous works. This is a state-of-the-art driving agent on the CARLA leaderboard. I'll talk about what that is in a bit. So this is sort of the main thing I did in the past over the last couple of years. Then I want to talk about a general idea of imitating algorithms, which I've seen coming up quite a lot in many robotics tasks. It's very similar to what we do in transfuser. So I'll kind of show what the link is between these works and why I think there's a very powerful way to do some visual control tasks. And finally, I want to talk a bit about data-driven simulation. So Hafe mentioned that I'm organizing some workshops. This is also a bit related to that. There are some new tasks, challenges, and ideas coming up in self-driving research and also broadly some robotics problems. And I want to briefly talk about what these are and what I'm going to be doing in the future and like right now towards that. So at any point, if you have a question, if you want more details on something, just pause and like I'm happy to discuss in between as well. Okay. Yeah. So let's start. Yeah. So we have a big team of people with Andreas, and the people working on self-driving who also contributed to some of the work I talk about today are me, Bernhard, and Katrin. We are the main PhD students in Andreas's group working on this. Then Aditya and Zahal, they are now doing some other things, but they worked on the transfuser project in the beginning. And Andreas is our supervisor. So I like to show this video. Hafe and Gaga have seen it, but for the rest of you, this is a parody clip. It's called Autonomous Intersection in Action. Sadly, the title is covered up with the Zoom thing, but let's just watch it. It's a 30-second clip, and it's from 2008. So, yeah. Who thinks this is real? Does anyone think this is real? Does anyone think this will be real in the future? Okay, so yeah, this was some CGI. So if you look closely, you'll see that like the pixels of these cars are exactly the same. It's just cleverly overlaid to create this effect. But the reason I show this is because I think like autonomous navigation can work fundamentally in different ways from human navigation, because the way these like systems work and how they interact can be very precise. And we could like probably not have this in the future, but I think have some superhuman transportation capabilities, and we could have different kinds of transportation than what we currently imagine the future will be. So we are obviously not anywhere near these kind of systems. What we work on is much, much simpler. It's called the CARLA leaderboard. So we have this task where you have a simulator called CARLA. It is based on a game engine, so it's based on Unreal Engine. And you need to navigate within the simulator from a start point, where it's this blue dot here, to the destination, which is in orange here. The car goes through like diverse towns and routes, and the average length of this route it needs to complete is somewhere between 1.5 2 kilometers. So this is quite long. And the interesting thing about the CARLA leaderboard is that they introduce some challenging scenarios for the self-driving vehicle to solve, which are specifically designed to be hard for humans. So they mind the most common causes of traffic accidents. These are some examples. Maybe like one intuitive one is like unprotected turns, or when someone enters the intersection when they shouldn't, like jumping a red light. So you have a series of such scenarios that occur at different points along this like 1.5 kilometer route, and you're scored on a set of metrics over like this cloud evaluation. So you create an agent which can take in sensor outputs and output actions like steer, throttle, and brake. This is run on a simulation server and evaluated, and you get a score back. So one nice thing about this leaderboard is that there is a held out set of towns, and this is fixed. So all the agents that are evaluated will undergo the same scenarios. They drive through the same routes. So even though it's not ideal and it's very hard to evaluate self-driving, this does bring the sense of a benchmark where you can compare different methods and analyze the strengths and weaknesses relative to each other. Right. So let's look at what you're evaluated on this leaderboard. The metric is on the left here. So there are n routes. This is 100 routes for this leaderboard. You have two terms that make up the metric. The first is a completion term. This is simple. This is how far you got to your destination in terms of distance along the route, and it's a percentage. So the best you can get here is 100. The second term is a penalty. It's like described in more detail here on the right. Here, what you do is the team that designed the CARLA leaderboard have like heuristically assigned some infraction values for doing things which are not allowed for safe driving. So if you run red light, you crash into a pole or something, or you crash into another vehicle, each of these things is considered an infraction. And then they apply a multiplicative penalty every time you commit one of these infractions. So as an example, the penalty for colliding with a vehicle is 0.5, let's say this. And that means if you get to your destination without colliding, your score will be 100. But if you collided once, it'll be 50. And if you collided twice, it'll be 25, 12.5, and so on. So this gives the teams always some gradient of progress. So if their agent gets better, they will get some difference. It's not very binary like a 0-1, but it also is like very strongly penalizing these infractions. So it's important to minimize these, even at the cost of sometimes like not completing the route. All right. So we wanted to work on this challenge in 2019. At the time, we didn't have like a lot of experience with like this visual control stuff. We were just getting into it. And the question was like, how do we work on this leaderboard? The most like well-established way to do this is a modular pipeline. You maybe like know some things about the task. You're supposed to drive in the center of the lane. You shouldn't collide with things. You should follow traffic rules. You can design some perception systems that identify all of these properties and write like some control logic that says do this when this happens. So this was one idea, and the other was to use reinforcement learning, where you basically like try to assign scalar reward values for different good and bad things that this car can do. and give it time in simulation to figure out what actions lead to good rewards. What we worked on was imitation learning. This was at the time also like quite popular in simulated self-driving. So before the CARLA leaderboard came out, there were some works on CARLA and many of them used imitation learning. The main reason is the simplicity of the method. It's also like quite difficult to do both the modular pipeline and reinforcement learning when the task specification gets more and more complex. I talk about what I mean by that in a second, but the main reason we worked on imitation learning is like the overall simplicity of the pipeline. So how we do imitation learning, it's also a bit non-standard. So normally you just have a human demonstrator who does a certain task. You record the demonstrations of the human and learn to copy this. But for our setting, asking a human to drive these cars in CARLA would also be quite like time consuming and expensive. So we do need like a few hundred hours of data to get reasonable behavior across all these different towns and layouts and scenarios that we need to solve. And so we went for this other idea of like trying to design the expert ourselves. And the first step to do that is like, because it's very hard to write out code on how to do the driving task from camera and LiDAR inputs, we instead create a simpler representation of the task. So specifically what we do is that if you have a driving scene like what you see here in the middle, you can kind of abstract away all the details that come through rendering or through like some process that relates to the visual sensors and keep only the underlying minimal information like the positions, speeds, and orientations of vehicles or the route you need to drive along, and try to write a policy that uses this abstract input to solve the task instead of using a higher dimensional input that you need to do in the end. So what happens once you have this abstract representation is that you can apply some well-known or like some very well-established techniques to solve this task in a near optimal way. So because we have this like perfect representation, let's call it, you can compute a optimal path in terms of distance to reach this destination. This can be with like A star or Dijkstra, for example. You just need to define what your notion of distance is between the points along this map, which you have access to in the simulator. And also doing things like following the traffic rules is quite easily achieved by using model predictive control. Here, the idea is that you have a simple model of how things move. And because you can extract the exact position, speeds, orientations, yaw, and so on of all the other vehicles from your simulator, you can forecast them into the future and evaluate different candidate actions for your car to see which of them lead to collisions or infractions and which of them do not. And then you can combine these to come up with a like basically a long Python file, like maybe like 500 lines or 1,000 lines of Python code that can solve the CARLA benchmark to quite high accuracies, not human level accuracies, but good enough to consider as a option for collecting a lot of data with. So you now have this expert policy that can generate a lot of data for you. And then the third step is basically what I mentioned earlier. You drive around in CARLA, you randomize the weathers, randomize the towns, like make more or less traffic densities in different areas. So you cover a wide variety of driving situations basically, and you collect the sensor data that comes with this expert driving around. I just show some images here, but we also have LiDAR sensors. So yeah, this was kind of an overview of how we get our data set. Once you have this, it's supervised learning to predict some representation of the actions that this expert policy took, given your input sensor data. So this is one of the state-of-the-art methods for this CARLA leaderboard, which we worked on last year. It's called transfuser, and there's a bunch of different blocks. So I'll step through it from left to right. We have on the left the sensor input. So we have RGB images and LiDAR scans, which we rasterize into bird's eye view. We have some height channels basically, and the second block is the sensor fusion and the processing of this input data. So this was actually something we found to be a critical design choice. And the thing that we did, which was not quite common in earlier methods, was we did this sensor fusion via transformers. So we had two convolutional networks applied to these two sensor modalities to generate grid feature maps. And then at different stages in the architecture, you would tokenize these feature maps and pass them through some self-attention layers of a transformer. And the goal of this was to introduce some global reasoning across modalities. So often we observed in the data set, there are situations where there's like a traffic light, which is only visible in the camera, and a set of vehicles, which is only visible at some point in the LiDAR precisely, that you need to model the interaction between to decide whether to enter an intersection or not. And in order to do this, like having a transformer for the fusion was, like I'll show you some results in a bit, a much superior choice to what traditionally people did here, which was doing geometric correspondence based feature fusion. So this is the fusion part. Then as we move to the right, there are different outputs you typically use for self-driving. The branch through the middle is the main task of the network. And here it is to predict waypoints. So waypoints are future bird's eye view locations of your car. So you say like, in 1 second, I want to be like half a meter ahead, and in 2 seconds, I want to be 2 meters ahead. This gives a notion of your future like speed and acceleration, which can be converted into the steer throttle brake output that CARLA requires using some like hand-tuned controllers, which are quite robust actually. You don't need to spend much effort on the conversion from waypoints to actions. There's also like a bunch of these decoders above and below. So these are auxiliary tasks. We basically make this overall architecture also do some perception tasks like depth and segmentation prediction or mapping, so predicting where the roads are, and 3D detection, so predicting bounding boxes in this bird's eye view space. These auxiliary losses are important for small scale experiments is what we found. So when you don't have a extremely huge data set with millions of samples for training the whole network end to end for your main task, it helps quite a lot to use the simulator to extract these extra perception labels and train your model to have like good, strong features that do these tasks related to driving. And then eventually, basically, you have like these features working together to predict the waypoints which you use to control your vehicle. All right. So some quick results of this transfuser approach. I mentioned these three metrics earlier. There's this overall driving score, which combines a completion term and a safety related term. So we have a couple of baselines here. which are late fusion, where you just don't have these transformers, it's just image branch and BEV branch. And geometric fusion, where instead of the transformers, you have a warping between perspective and bird's eye view space based on the camera parameters and LiDAR intrinsics. So both of these methods are like what used to be sort of popular in perception tasks. So this is what people did a lot for detection or bird's eye view segmentation or 3D detection from camera inputs. The thing we observe is that in terms of completion, for example, the geometric fusion transfuser, which is our approach, and at the bottom is the expert demonstrator, which is this MPC approach I told you earlier. That isn't directly comparable because it's not using sensor inputs, it's using the simplified input. They have very similar completion. So that means like in terms of following the route, all these methods, so also the geometric fusion is expressive enough to convert this like road layout into the bird's eye view space where the route needs to be predicted. But when it comes to this like safety related metric, which is like how often you collide or make red light infractions, having this like global reasoning that comes with the transformer modules does lead to a significant improvement. And then we also see that this is the main like remaining challenge for solving this task and reaching the expert's performance. We are still quite a bit away from reaching this 0.86 or so of the safety metric. And also, if you look at human performance on the same task, I think you can even get the safety to 1. So it means like clearly these models, like even though these scenarios they are being tested on are very challenging, like where you have like people running red lights, jumping into your like in front of your vehicle all the time, it's still like not great that you get an average score of 0.5 on safety. So we need to get much better basically. This is a snapshot of this CARLA leaderboard. So I mentioned that there are these challenges. We started working on this in 2019, and the first challenge was in 2020. The table I'm showing here is from the 2021 challenge, and there was also one in 2022. So in 2021, we were like second place and just barely. So we missed it by a point. Yeah, it's like maybe our method was slightly worse at route completion, but better at avoiding infractions than the winner of that year. In the following year, though, in 2022, we did a lot of engineering improvements, so we didn't fundamentally change the method much. And this one of the tracks of the CARLA challenge a few months ago. So yeah, I think like this kind of concludes this first mini part of the talk. So if you have any questions about this, I'm like happy to take them now, or I would move on otherwise.
One quick question, like how these metrics are dependent, like that you can do like if you're doing better in driving, you can also do better in completion and also so that is the dependency between the different metrics.
So there is a weird interdependency in that if there are situations where if you try to maximize completion, you get a lower score because you just encounter more of these challenging scenarios. And maybe like one of the most challenging scenarios is at the end of the route and you crash in this one. So it's like a bit weird, and the model which actually gets further along the route gets a much worse score because of like encountering this like challenge at the end. And this is something that like people are aware of. So like this is why we always report all of them together, and we also like show like qualitative results and like show like some other reward based metrics sometimes. But I think it's hard to have like a single metric that fully encapsulates good driving. So having these like multiple axes is kind of the current solution.
So if I have to conclude, like, so I see a lot of work regarding end-to-end based method. So in that case, of course, we are trying to define a single loss function with interdependent and several kind of loss. However, this is technically make me believe that a modular is the right way to go.
So I think when you use a modular approach, the disadvantage of the modular metrics is basically that you're potentially optimizing for something that is unnecessary, like the precision of the 3D box of like a vehicle 50 meters away. And I think like something in between is now gaining more popularity, where you have a modular stack, but all the modules are optimized somehow for a proxy of the driving performance. So you have like some way to know like which detections are more important for planning or which forecasts are more important for planning. And you prioritize these while training the modular systems. So yeah, that's what I would say is sort of the direction things are going. Right. Yeah.
Question regarding the inclusion part of the architecture. You showed the pipeline for two different modalities.
Yes.
The RGB images and the peer-to-peer library.
Yeah.
Have you considered how this approach and the design choices that you have made scale to more modalities, to a higher number of modalities?
Yeah, so I think the high level idea is just to disentangle the modality specific processing and the modality agnostic fusion. So if you add another modality, the main increase in parameters is two things. There are more tokens for your transformer, and you have an extra branch for that modality, right? So like we often get asked like what happens if you have more images than one image, right? And then the like so far what we've also tried like many setups with different kinds of like counts of images and like 3D lidar and so on. The main thing that we need to take care of is the number of transformer tokens. This has to be kept reasonable. The per modality processing is not that expensive relative to that. And then when you have like this limited budget of transformer tokens, it's really like that's where you decide like which modality gets like how much precision. So you can like, for example, sacrifice some precision in the LiDAR BEV by reducing it to just like 16 tokens, and they have like coarse cells. But because you also have this BV branch that does like a finer processing of these like large tokens, you can kind of get away with that. So I think like we currently scaled this to things which have like 400, 500 tokens without much problem. But I think like just naively adding modalities and using like small cell sizes would not work. Yeah. All right, so let's move on. Yeah, so the next thing I wanted to mention is that this idea that we used in transfuser that I stepped through is actually like quite widespread, and it's not explicitly called something. So it's not called like reinforcement learning or imitation something. It doesn't have a technical name, but I've seen it on the top left here. This is from ETH from Marco group, is the winner of the DARPA Subterranean Challenge, where you send these robots underground on a search and rescue mission. This is the one of the, I think it's the best systems paper from Coral, which was in December. This is a off-road racing challenge, and there's some other work on CARLA on the CARLA leaderboard. All of these methods use the same idea of imitating an expert algorithm. And like one specific example, which I think is super impressive, there's a video also from Zurich from last year of a human versus AI drone race. And the human pilot here is a former world champion of drone racing. So they put on these VR headsets and drive them at crazy fast speeds. I think they go at like 20 meters per second, which is 70 something kilometers per hour. So this is really fast. And The really interesting thing here is that, like, okay, maybe anyone wants to guess which is the AI drone and which is the human drone out of these two. So there's the orange one and the blue one. Any other? Okay, there's only one answer option. So the actually, like, I also forgot. So the AI one. So the one which finishes first is the AI drone. Basically, it does like much more aggressive and sharp maneuvers. And yeah, this is a vision only solution. So it's like camera only input and control outputs for these quad rotors. And yeah, the way they do this is exactly the same as what I just showed you for how we did the CARLA challenge. They abstract away the task into just these gates. So they model these gates in a simulator that the drone needs to follow. They have like optimal path planning, like a time optimal path. They don't use like A star like we do, but it's like based on some quadrotor math. And yeah, they also use model predictive control. I didn't find a good image with a drone in it. So there's a car, but yeah. And then the final step of their method is also simulating a lot of different gate layouts and trajectories, collecting sensor and trajectory paired data, and training a very fast sensor-based end-to-end policy to generate these actions given the sensor input. So what I'm kind of getting at is that I showed you some results with quadrupeds, some with drones, some with cars, and all of them use this high-level strategy of imitating a privileged planner. So you start on the top left where you have some complicated real-world representation that you can extract with sensors like the camera, but you first create like a offline abstract version of the world. So you can do this like with human effort or with algorithms, but the idea is you simplify the task down to the task relevant details and build a planner that uses this abstract representation to solve the task to like a near optimal solution. And once you have this bottom branch, this is basically acting as a label generator. So this tells you what action to take in a corresponding, like in a sensor reading that corresponds to this representation. And you can train a end-to-end policy that imitates the behavior of this like abstract planner. So there are a couple of advantages of this setup. The first is that the whole branch on the bottom does not have any real-time constraints. So you don't need to build like a very fast planner which like needs to discard certain future possibilities and only focus on the important ones. You can really go like in this brute force way and use all your offline compute to generate this label data you need. And this doesn't affect your runtime of your final policy because you're only using this planner to provide labels. You can also do the same for generating your abstract world representation. You don't need like a real-time map generator or object detector, for example, in this scene to do it. You can maybe drive a car multiple times through this intersection and fuse all that information that you gather through these multiple drives. Or you could use multiple cars, for example, in cooperative setup to generate this representation. And you can do things like I will show you in a bit. Like there are some cool tricks you can do in this setting where this entire bottom branch is detached from real-time requirements. Okay, so yeah, on to the last part. Maybe a quick guess, if anyone can. Where is this taken?
Las Vegas.
No, that was good. Yeah. So this is the Paris Casino in Las Vegas. And so these days you can make like I mentioned like doing this thing with a multiple drives through a intersection, you can reconstruct it. So with multiple drives through Las Vegas, this is something from Google Maps. You can basically like reconstruct very dense maps of areas you have covered multiple times. And this is the same scene. On the left, I show the Google Maps image. And on the right, this is a frame from a data set called nuPlan, which I talk about now for the last few minutes, where you have these auto-generated maps for all of the routes that this car drove around. It's around like 15 hours of a car driving through different US cities. And besides just these maps, the interesting addition to this is a bunch of 3D auto labels. So you have 3D bounding boxes for vehicles, pedestrians, static objects. All of this is generated on their big cluster. So they just collect the sensor data in the drives through the city. They gather all the sensor data and they use like these offline perception methods, which basically combine ideas from detection and tracking and do a lot of refinement at a per object level to give you some precise bounding boxes that are completely automatically generated. And once you have this, you can take the scene, you can insert all the vehicles you saw, that's in green. The pedestrians and static objects are in blue and purple. You have like also through observation of how things are moving, a way to extract traffic light states for different blocks of this map. So the green dots indicate that there's a green light to pass through this block right now, and the red ones are for red lights. So essentially what we have done now is, if you remember this like diagram I showed you of like abstracting the world and creating a planner, you now have data sets which can, like without human effort, create this abstract representation of real world driving scenes that looks like this. And once you are here, there's also a line of research. There's like not from the nuPlan simulator, but this is, I think, from Wave. And there's also like many other ideas in the space of how to move vehicles and pedestrians in a simulated world. Like once you have this sort of representation, you can give all of these actors some realistic objectives. They need to reach a goal and they need to do it in the least time possible or while maintaining very high safety and so on. And you can generate diverse behaviors this way. You can, through like this, basically done through some multi-agent reinforcement learning, or some like there are some hierarchical imitation learning type algorithms that you can apply this policy on all agents or some subset of the agents in this town and make them drive in meaningful and diverse ways, such that you now have a way to, starting from raw sensor data that you just collected on your data collection vehicle, create a simulator that has other actors. It has realistic road layouts. It has like lots of diverse behaviors. And this is basically this platform you want to build your planner, this expert policy, which can solve the task in this simplified representation and then give you some supervision on how to do the task in the real world as well. So I think like the reason I showed this nuPlan in particular, even though there are many different ideas in this like data-driven simulation area, is that there is a nuPlan challenge, the first version of the nuPlan challenge, where I'm co-organizing the workshop that hosts this challenge. This happens at CVPR this year, and the challenge has a deadline in May or so. And the task here is to build planners that can complete routes similar to the CARLA leaderboard, but rather than using sensor inputs, doing it in these like abstract versions of the real world. Yeah. So yeah, this is maybe the last set of summary slides then. We talked a bit about imitation learning on CARLA. We showed that this imitation of an algorithmic expert is the state of the art for the CARLA leaderboard. We have released the code and like all the different tools for generating data, generating scenarios, like all the different scripts we used in our CARLA solutions on that repository. Also talked a bit about nuPlan, which I think is a very exciting new challenge and direction, which sort of brings some aspects of realism into this kind of closed loop self-driving setups. And that's the code and the dev kit if you're interested in looking at the challenge. And I also wanted to quickly mention some other work which I didn't get to talk about right now, but I'm happy to talk about if anyone is curious. So there is NEAT, which is a method that does bird's eye view predictions of semantics from 2D images. So it does this classification of bird's eye view locations into road, sidewalk, person, vehicle, and so on. And the thing that we did different here is we did it via neural fields. So instead of having a grid representation in bird's eye view, we have an implicit representation. And this is like carrying over all the pros and cons of implicit functions. So lets you have like very high resolution. We also use this to model like temporal semantics. So it lets us do like very like high dimensional prediction with a very small network. And we also demonstrated that on the end-to-end driving task, doing this bird's eye view prediction task as an auxiliary loss can improve the safety metric a lot, which I talked about earlier. We had a paper on, it's called King from ECCV, and this is on optimizing your data set. So a very crucial aspect of all these imitation learning ideas I talked about is where exactly you source your data, because you have this simulator and you could go anywhere in your simulator and generate all kinds of scenarios. So one thing we did in this project is we explicitly optimized our data set. So we parameterized the positions of other vehicles with a small set of like 8 to 10 parameters that describe the trajectory the other vehicles take. And we optimized this data to induce near collisions with the ego vehicle. And doing this gives you like a very rich data set that makes the policy you learn much better at avoiding collisions. And lastly, we had this work called Plan. This is a planning transformer. So we don't use sensor inputs in this work. We directly use object inputs. And we try to study what happens when you learn a policy with a transformer architecture instead of CNNs, which are more common. And one interesting property we saw is that the attention weights of these transformers tell you what object is most relevant to the policy's output. And we have some qualitative metrics and quantitative and qualitative results there that show that you can kind of use these attention weights to get some explanations from these transformer-based planners. Yeah, so with that, Hafe also mentioned this. We have a couple of workshops. There's the CVPR workshop. Definitely check out the challenges. It's called End-to-End Autonomous Driving. We have 4 different challenges. They're all on newly emergent tasks. One of them was nuPlan. There is a occupancy prediction challenge, which is like predicting 3D occupancy from camera inputs. There's a topology construction challenge, where you basically need to identify the relationships between traffic lights, traffic signs, and roads, and so on. And we have an online mapping challenge where you have your camera and LiDAR data, and you need to construct HD maps on the fly and not in this offline way. So all of these are things that are recently gaining interest, and we hope that these challenges, there's a lot of prize money as well, will attract more people to work on them. And another final, this is the last slide. We also have this iClear workshop. It's called Scene Representations for Autonomous Driving. Here, we wanted to try something different in terms of the scientific publication format. So you can submit to this workshop a research insight, which is not original work of your own, but rather a commentary or analysis of someone else's work. So you can submit not only a written analysis, but if you've re-implemented some method, you can submit the code of the re-implementation or a blog post or like your standard paper as well. And you also have the option of just submitting a workshop paper, which is an original contribution in all of these formats. So yeah, we hope that we get some interesting submissions because of these new formats. So yeah, this is it. Thanks a lot for having me. And yeah, if there are any questions, I'm happy to answer now.
Okay, thanks for a very nice presentation. I'm actually very curious about safety issue. How did you make a safety issue in the community?
Safety in the King work.
Yeah.
So
But do you explicitly optimize for the safety events like collision or whatnot?
So this is explicitly for collisions. Basically, what we do is we run an optimization to induce collisions of the current policy.
Mhm.
So you can think of it as some sort of adversarial setup. You're optimizing the data set to make your policy fail,
Okay,
and then you optimize your policy to not crash on this data set iteratively.
but how does your network know that collision is a bad event?
So what we do in between these two steps is basically once we optimize the data set, we also extract expert labels for this data set. So for this trajectory, we have like this rule-based expert policy, which I mentioned earlier, which knows that the optimal strategy is to not crash. Like this is known through its model predictive control. It gets a very big penalty for colliding.
Okay.
So the idea is like more to adapt your data set to the final imitation learning agent, which is going to learn from it. But the data set itself is labeled still by some privileged policy.
Oh, okay. So in this one, your agent will see some very case and then.
Yeah, and yeah, so even though this is a failure case of the agent itself, we still want the expert policy to not fail on this. And this is the data that gets added to the data set. Yeah.
Thanks.
Question, I have a question on the nuPlan challenge. What's the scale of the data set that you collect in terms of metric, like hundreds of kilometers?
So I don't have the kilometer number, but it's 1600 hours of driving. And if you just collect the logs, so the whole data set in where do I have it? The whole data set in this format, no sensor data, is 2 terabytes of data. Yeah, so I didn't talk about this today, but I'm also working on some compression for this. So you can, in principle, build a generative model to store all of this data instead of storing it as raw, like logs. And this probably makes it much more convenient to work with and share.
I think for the next slide,
Yes.
like I like this visualization for sure. Question is like, how did you scale it? Like if it's like what's the transformation we're doing from a real world map to this graphical user interface to kind of
Yeah.
much convenient and compact.
So I think like this is not one of the nuPlan real world maps. This is a like procedurally generated map based on some rules that makes it nice for visualization. But when you do this on a real map, basically what you do is you isolate a region and you don't simulate anything outside that region. So the other actors are still kind of in place everywhere outside, but you're only adaptively simulating the part which your car is passing through and holding the rest frozen until your car reaches that point.
And also, it's not just about imitation learning framework, that's where the base action for imitation. And do you think this kind of recognition also based on transformer happening?
So like I think the like for us, always the challenging part for reinforcement learning was not the reinforcement learning itself. Like if you apply PPO at some scale, your policy will do what its reward function specifies. This is working with the abstract representations we use. The problem is actually specifying the rewards for us. It's like much harder for us to specify a good reward function compared to writing this expert MPC policy. The MPC costs, like when you directly use them as rewards, the learned policies do optimize this reward very well, but in weird ways, which we don't want. So like one example we found is that when we wrote an RL policy, it just learned to drive very, very slowly, which gives like really like this, it's like a local minima in the cost. Some other weird stuff like this. And the second thing is also it's just like the it's harder to add functionality, which we often need to do. So the CARLA leaderboard often adds like new subtasks, like you need to give way for emergency vehicle in the new version. And then it's easier to have a rule for this in our expert policy, just written in Python, like if open bracket, there is an emergency vehicle so many meters away, do this, than creating a reward function, which encapsulates this like behavior of making way for an emergency vehicle and stuff like that. But I think like imitation learning and RL are also much closer than they were before. We have like played around with some offline RL, which is kind of like imitation learning, but you also have some bad examples, which are marked as like the reward is bad here. And I think like, yeah, it's like the main factor that I think makes RL hard is like this specifying the reward, but the actual like tools we have are good enough to work with these representations.
One question on sorry. There's lots of good work here. On the neural field work that we have done, it's more about tensor representation. And I think, could you shed a light on like why we tensor representation for driving?
Okay. Yeah. So I think like driving has like fundamentally these two disentangled things that you need to do. There's like the basic geometric collision avoidance. So irrespective of what object it is, if something flies in front of you, you need to avoid it or stop or so on. And then there's also the more like semantic planning. So you need to know how a person would move given their pose or stuff like this. I think these two are very different things. And neural fields actually help a lot with the more geometric side of things because like if you voxelize your word based on your memory constraints into like 50 centimeter cube voxels, you can't capture certain geometric properties well. And this is where like I think having a neural field representation lets you do this in a somewhat like meaningful compute budget. So this particular work, like we stopped using it in our like challenge submissions because like one thing we observed is that for our particular challenge, as you scale up the data set a lot, these auxiliary tasks actually start to matter less and less. So your model does get better by just scaling the data set and only training it for the end task of predicting waypoints. And the auxiliary tasks were actually only much more helpful in some of the earlier settings we used where we had smaller data sets, and having this like features that are aware of the 3D structure of the world could bring quite some benefit. So I think like, yeah, maybe this was not like a precise answer.
No,
But,
and then
yeah.
of course, because I'm also struggling, like if I, so where this fits into the equation of using other neural fields and other design. So
Yeah, so-
it's still I'm myself is struggling with that.
I think like it's going to be eventually part of this like not long-term planning, but the very short-term collision avoidance strategies for like making these like very like time constrained decisions. I think it's also like if you have watched Tesla's AI Day talk, this is something they use for their like occupancy predictions. They don't predict, so they have like a grid of features, but the actual final predictions are made via a neural field. And the nice thing about them is like you can always like query just the center point of each of your voxel features and recover like the explicit representation. These like MLPs that people use are like usually like 2-3 layers of 256 units or something. So it's not so hard to just like use all your explicit techniques as well on top. It gives you a way during training though to be more precise because you can sample very precise boundaries of objects and so on for supervising by training.
Very nice. Very nice. By the way, so Kasia is also here in afternoon. If you want to have some discussion, you can reach out to your.
Yeah, I'm happy to do that.